Hi, this is Nick LaRue, and I'll be presenting about the element distinctness problem. So the problem itself basically asks if all n elements in a given array are distinct, meaning, of course, that if we have two elements in the array that are duplicates, that means that this given algorithm would return false. So if we had two twos in an array, it would return false or no in this situation. The model of computation is comparison, meaning you can compare two numbers x and y in constant time and answer if x is either less than y or equal to y or greater than y. And what we're going to seek to prove is that you cannot design an alternative algorithm that runs faster than n log n time. So the way we're going to sort of set up this problem is by interpreting an array x as equaling basically some points in a n-dimensional space. And our vectors will be between the values of 0 and 1. So here we kind of diagrammed out a sort of a two-dimensional example. So as you can see, there's a red line there, and basically any point we're going to have is going to take place on either side of that line, because we cannot have duplicate values. So if you look here, for example, if you have 2 points that are duplicates, for example, 4 and 4, they'll end up meeting on that line here. Of course, again, this is just one example. If this was a two-dimensional space, but of course you can have up to infinite number of dimensions, but it's still the same rules apply. So basically, what we're going to seek to do is to try and prove 3 different claims. The first one is let a region R of L, where L is a leaf, be connected. The second is, given a vector x consisting of distinct elements, let a vector y be a non-trivial permutation of x. X and y must reach distinct yes leaves. And the third one is number of yes leaves is greater than n factorial possible solutions. So let's look at the first one, the first claim. Let a region R of L, where L is a leaf, be connected. So what we want to do is realize that instances visiting any yes leaf form a connected region in instant space. And one of the ways we're gonna prove this is by basically proving that R of L is a convex region. Now, a convex region is defined as basically, if given a region R, is said to be convex if for any points x and y in R, the straight line, that's an important part of that, the straight line path from x to y passes entirely through R. So if we look here, basically, this is a cube convex region. And so if we have 2 points that connect them, we can draw a straight line from one end to the other and still be within this region. If x1 was here and x2 was here, then of course that'd be considered outside of the region, and this would no longer be true. But we're going to try to prove that if R of L instances for which leaf L is reached on execution, R of L is a convex, is a convex region. So the way we're going to do this is basically creating 3 different instances. We're going to have an instance we call X, where our leaf L is reached. Execution 2, where it also reaches the same leaf. And execution 3, that also reaches the same leaf. And we're going to define z or zeta by this function right here. Now, basically, lambda is going to be between numbers 0 and 1, including 0 and 1. This means z is on a straight line of x and y. That's what we're going to try to prove. So for here, basically, if you look at this equation, 0 equals y, 1 equals x, And in between 0 and 1, we get the midpoint of x and y, meaning again, that z would be represented on the straight line of x and y. So if we, for example, imagine sort of a root of I and j, and we use the less than branch taking execution 1, that would mean that the less than branch would also be taking execution 2. So this would basically mean that xi would be less than xj, and yi would be less than yj. And so if we actually sort of take this equation from before and we plug in the xi and yi values and the xj and yj, we actually can see that that this still holds true for xi and zi and zj, zi being less than zj. That means that since we also have the less than branch taking execution 3, that means that R of L is a convex region. So that proves our first claim. And so now we're going to look at the second claim. Given a vector x consisting of distinct elements, let a vector y be a non-trivial permutation of x. X and y must reach distinct yes leaves. So the way we're going to do this is by proof of contradiction. We're going to assume x and y reach the same yes leaf L. So now we've proved that R of L is connected. This means that every path P from x to y is entirely through L. So we're going to try to show that there's a permutation Z in P that leads to a no leaf. So the subclaim, which we're going to try and prove later, but for now we're just going to take it as a matter of fact, is there exists I and j such that xi less than xj, while yi is greater than yj. So if we define a function f of w, where we have w of y minus wj, what we'll see is that f of x will end up being less than 0, and f of y will end up being greater than 0. So if we refer to the mean value theorem, we know there exists a z in P such that f of z equals 0. So now that the path is continuous and f of w is a continuous function. So when we get f of z equals 0 and z of I minus z of j, we also get 0, which would imply that z of I equals z of j. This means that they are not distinct elements and therefore cannot be in the line xy. And so z and p is supposed to lead to a no leaf, and therefore we get a contradiction. Now let's go to our subclaim right here, just to make sure that this proof by contradiction is actually complete. So here our subclaim is there exists I and j such that xi is less than xj, while yi is greater than yj. So if you look at this graph here, we basically have our x values here, and then we have our y values as well that are connected to our x value here. And then below we have our pi values of x. So essentially what we've done here is we've sorted the x values here through this function. And so now it's in ascending order from least to greatest. And then we've taken the y values that have mapped the x values along with us. So we have 0.5 for 0.2, we have 0.7 for 0.4, etc. And so if I is less than j, we can actually conclude that pi x of I is going to be less than pi x of j, as we can see here. 0.2 is going to be less than 0.4, of course. We know y cannot be increasing because if I is less than j, then pi of yi must be greater than pi of yj. So if we remap these back onto here, we see that this statement actually still holds true. So now we've been able to prove our first two claims. And so basically what that gives us is we realize that if both of these holds true, then we have distinct yes permutations, and the number of that is going to be n permutation, n factorial. And so we cannot have anything better than n log n, because as we know from the sorting algorithm, that if you have n factorial permutations, that ends up, because of the height of the tree, it ends up translating to n log n as our big O notation, our worst case solution. And therefore, we've settled all of our claims. So this has been the element distinctness problem, solving for the lower bound. So I hope you enjoyed that presentation, and thank you for your time.